All right, this is going to be part 4 of chemical equations, classifying chemical reactions. So at the end of this, what we want you to be able to do is classify chemical reactions, but then also we want you to be able to predict the products of a chemical reaction. And this is really important and one of the skills in chemistry that I think is probably one of the most important because as a chemist, when you put two things together, it's really important that you know what you're going to get. And the main reason is so that if you get something that could be dangerous or could be a safety hazard, that you either don't put those two things together or that you go about the correct safety precautions. So again, classifying chemical reactions and also being able to predict the products if we put two things together or more than two things together. So the first type of chemical reaction is called synthesis, the direct combination of two simple elements or compounds. So you can think of this as A plus B equals, well, those two things together. So a good example, if I scroll down, would be maybe sodium and chlorine. So if I add sodium and chlorine together, I get something a little more complex, which is sodium chloride. If I add hydrogen gas and oxygen together, I get water. And then if I scroll down to this example here, if I want to predict the products, if I add iron and oxygen together, I'm going to get iron oxide. And it's important to note that oxygen is -1, and I'm getting that just from my periodic table of ions. And iron is actually +3, at least the version we are in this chemical reaction. And so if I crisscross and drop, the 2 goes here, 3 goes here. And if I'm going to balance, I'm just going to put a 2 right there. And this chemical equation is balanced, and I predicted the product of that chemical reaction. The next one is a little bit tricky. It'd probably be easy to say that CO, carbon monoxide plus oxygen, is CO3, but that actually doesn't exist. This produces CO2. If I'm going to go back and balance this chemical reaction, I think I'm going to put a 2 right here, and that way balance. And again, I'm predicting the products of what we're going to call a synthesis reaction. And so you can kind of think of this, and this is an analogy I'll come back to, but maybe mom and dad come together and they're maybe dancing partners. They're going to bond together. So the opposite of synthesis would be if mom and dad for some reason split up, they stop dancing with each other. This is called decomposition, or often we call it analysis. And if you think of analysis, that word just means to break down or to break apart, which is what we're doing. We're taking a complex substance and breaking it into two or more simple substances. And oftentimes it's considered an endothermic, or it is an endothermic reaction. So if we take carbonic acid and we break it down, we get water and we get carbon dioxide. And if we take sodium chloride or table salt and we break it down into its simpler parts, we get sodium and we get chlorine. And so a couple examples of predicting the products. If we took H2O and we broke it down into its two simple products, its two simple products would be, well, hydrogen and oxygen. So here's hydrogen, it's oxygen. And the one thing we want to notice is that these are diatomic elements. So if I'm going to put these products here, it's going to be H2 and O2. And then if I'm going to go back and balance this, I think I just put a 2 right there, and I should be balanced. And so this is the products of the breakdown of water. And if we did the same thing, we'd have mercury, which is Hg, and oxygen. And oxygen is a diatomic element, but mercury is not, so we're going to leave it alone. And then to completely balance this equation, we get 2. Okay. The next type of chemical reaction is going to be something called single replacement. And this is where things get a lot more interesting. This is where we'd have maybe a lone element, and it's actually going to come in, and if it's a positive or negative charge, whatever it might be, again, that's what's holding these two ions together, is one of these ions is going to switch places. The positive would switch places like that. And so what we get is B, or A plus BC, produces B plus AC. And you can kind of think of this as if mom and dad went to a dance together, and maybe somebody started dancing with another person, and they switched dance partners. And then one person was left by themselves, and the other person with the other person dancing. So it's kind of like one dancer gets bumped out for another. And so if we have an example, a good one is the second one here. We got zinc plus sulfuric acid. And so zinc is a positive charge. And again, I just know that because I'm looking at my periodic table of ions. And this positive charge is going to boot out the hydrogen, which is also a positive charge. And what we get is zinc sulfate and hydrogen gas. And so hydrogen is left by itself, and zinc is then bonded to the negative SO4. And so if we do, we've got 3 examples here of predicting products of these single replacement reactions. And so zinc, again, is positive, hydrogen is positive, and chlorine is negative. So what's going to switch, and this is the part that maybe some students get tripped up on, it's going to be the 2 positive ions. Because again, positive attracts to negative. We're not going to have 2 positive ions attracted to each other. So what we end up getting is zinc chloride plus hydrogen gas. And zinc has a +2 charge, chlorine is -1. So the 2 goes down here. And then I can erase this here. And if I'm going to go back and balance it, I believe we're good. So if I do the next one, again, this copper is positive, silver is positive, and then NO3 nitrate is negative. And so what's going to switch? It's going to be the 2 positive ions, so it'll be copper nitrate, parentheses, plus silver. Copper nitrate, let's see, this copper has a +2, nitrate is -1. We crisscross and drop. The 2 is going to go out here. I'm going to erase these numbers here. And if I'm going to go back and balance it, it looks like I think I should be good, except for I need to put a 2 there to balance it out. And then we're good. We predicted the products. And the last one, chlorine is negative, and sodium is positive, and bromine is negative. And so here we notice we've been switching the first element of each one of these ionic compounds, or binary ionic compounds. And in this one, we're actually going to switch the back one. So if you know anything about naming, you know that the positive cation always goes first, and the negative anion goes second. And in this example, the chlorine is negative. It's going to switch with the back element, which is going to be our anion. So what I'm going to get is NaCl plus bromine. Bromine's a diatomic element, so Bl or Br2. And then to balance this, I think if I put a 2 right there, we should be balanced. So that is single replacement. And the next one is going to be double replacement. And if you can imagine, we've got 2 couples dancing. And what's going to happen is both couples are going to swap. They're going to swap a partner in exchange for the other. So we have 2 different atoms and 2 different compounds that replace each other. And that forms to create something totally new. So a good example would be, well, we have these 2 right here. So Mg, CO3, magnesium carbonate, and then hypochloric acid. And so we're going to have CO3, which is going to have a -1 charge. Cl is going to have minus. H is positive, Mg. And so these are just going to switch. The negative anions are going to switch. And so we get magnesium chloride and then carbonic acid over here. And then here's another example of that. But let's do one where we predict the products, because those are a little bit trickier. So we've got 3 examples here. And we won't worry about that one on the bottom. So potassium chloride, positive, negative. And then lead is going to be, if we see the 2 over here, we know that this is going to be positive, but which version of it? It's going to be positive 2, because there's a 2 right here. We reverse, crisscross, and drop. And then NO3 is -1. So what's going to happen is the negatives are going to switch. And so what we get is we get potassium nitrate plus lead chloride. Since lead has a +2 charge, we cross and drop. 2 goes there. And then I would just want to balance my equation to like that. And then we're good to go. And then we've got another example. We've got positive sodium, hydroxide's negative. And again, I think these are all +1, -1, +1, -1 charge. And so again, the negatives would switch. So it would be sodium chloride, or salt, plus HOH. And really, what this is H2O. But I like to write it like this because then I know exactly where that hydroxide group went. And then I go back and I make sure it's balanced, and I think this one is. So if I do the next one, ammonium is a +1. And again, I'm all getting all this information from my periodic table of ions. And so negatives are going to switch, so it's going to be NH4 OH plus NaCl again, salt. Make sure that it's balanced, I believe so, and then we're good. So that's predicting double replacement products and a double replacement reaction. So the last couple examples of types of reactions are going to be ones that are going to be just examples of what we already know. So acid-base reactions are really just an example of a double replacement reaction. And what we want to know is that when an acid and base are put together, what it ends up producing is water, always, and some kind of salt. The positive cation of the acid always is going to combine with the OH negative of the anion of the base of the water. So this is how we have our what we end up doing is we form a neutral substance that is the salt. So if you don't know much about acids, maybe if you think about what you eat, acids are the things that maybe cause it to be sour in your mouth, and bases tend for it to be bitter. Bases tend to be slippery, and then common acids would be like vinegar, carbonic acid, carbonation in soft drinks. These are acids you would see in your food. And then common bases would be like detergents and soap and lye. And if you've ever maybe had soap put in your mouth, if you've said something like a bad word, maybe you know that bitter taste of soap. So that's acids and bases. And again, it's just a glorified example of a double replacement reaction. So the negatives are going to switch with the negative, and it always is going to form water and then some kind of salt. And the salt's what's different, but it always forms water. And the last one is going to be combustion. And so with combustion, we always have something that has a lot of carbon and a lot of hydrogen. You're going to add oxygen to it, and then it's always going to produce CO2 and water. Always, 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 in every combustion reaction. They're always exothermic, so they're going to produce heat. And if you just remember the bluish bottle demonstration we did, the thing we burned was isopropyl alcohol. We added oxygen, and then it produced a lot of energy, carbon dioxide, and water. And so these are these 6 types of reactions. And then if you're going to guess the products of a combustion reaction, that's really easy because all it is CO2 and water. Always, 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 no matter what. So our 6 types of reactions are going to be synthesis, decomposition, single replacement, double replacement, acid-base reactions, which are just glorified double replacement reactions, and then combustion reactions, which always produce CO2 and H2O. Thanks for watching.